Okay, we're going to continue in this video. We're looking at circles and circular motion. In the last video, or in the previous video, we looked at linear speed and angular velocity. And those equations and those are differing values. And now we're going to look at acceleration and what acceleration is happening and what forces are acting in a circle in this instance. So, if I draw a circle on the board, and we have to imagine for a second a scenario for this one, that we've got, say for example, an object on a string that we're swinging around in a circle. So we're swinging it round in a circle, like so, and it's going round like that on a piece of string. Now, what is actually causing it to move in that direction? Well, when you do this, you might feel the force in your hands. And effectively, when you're moving this in a circle, you are pulling always towards the center. And that pull towards the center is the centripetal force. Okay? So that is the centripetal force. It's a force that's acting always at right angles to the motion. And that is true for every position on this circular motion. At this point, instantaneous point in time, the ball is moving in that direction, but the centripetal force is acting at right angles to it. Same here, and the same here. All the way around, that is true. The centripetal force acts at right angles to the motion. And that's what creates this circular motion. Now, when we're looking at this as a situation, we're saying, okay, well, the force is pulling it that way, i.e., if we've got a force, what do we have? Well, we've got a force, we most certainly have a mass, so what other thing is missing from a force and mass equation? Hopefully you'll recognize it straight away. Acceleration. Now, is this accelerating? Well, yes, it is. It is accelerating all the time. It's constantly changing its velocity. That would be linear velocity. It's constantly changing its velocity because it's constantly changing direction. So we have a constant, what we call centripetal acceleration. And we have equations to help us work out centripetal force and centripetal acceleration. Centripetal force is calculated by mv squared over r, where v is the angular speed from last video. R is just the distance r there. So quite nicely here we can say what the centripetal force is calculated as. There's lots of good videos on YouTube deriving this equation and likely to be a derivation for it in your book as well. So I don't see the need in going through that now. Now there's also, as you may remember from last video, that there is another term for motion in a circle, and that's omega. And the equation for centripetal force for omega is m omega squared r. And both of these values are exactly the same. Force is equal to mv squared over r, force is equal to m omega squared r. These are both one and the same centripetal force, the force acting at right angles to the motion along here. So we have these equations, and we can actually then derive other equations from this. We can just pick them out more than anything else. Because we can now say, because force equals mass times acceleration, that the centripetal acceleration is v squared over r. And we can then also say that the centripetal acceleration is omega squared r. And we now have a lovely bunch of equations that allow us to work out not only the centripetal force here, but also the value of the acceleration, the value at which this is being accelerated towards the center of this circle. Obviously, it never actually gets to the center of the circle because we're maintaining the radius and we're maintaining this speed. And this is the force that will be required to maintain this speed, to maintain the circular motion. So let's have a look at these, some of these points in a little bit more detail about what the forces are actually occurring here. And over the next video or two, we're going to look at vertical and horizontal circles and some of the forces that are involved there. Now, one thing you need to be aware of in this situation is that if this is an object on a string, then this force effectively is going to be made up of multiple forces, especially if you're swinging it vertically, at different points in the circle. One of the most poignant points on this circle is right here. Because effectively, the centripetal force, is going to be equal to a mix of two other forces. What those forces are obviously depend on the situation. Now, we're talking about a ball or an object on a string. So we've got tension in this string. We've got a tension in this string pulling it that way. What other force would be acting in this direction when we are spinning it in a vertical circle? At this point, you have gravity, or the force due to gravity, pulling it downwards. So we can say that the force at this point, and we'll call this F1, is made up of a tension T1 plus mg. That's the force due to gravity. And quite nicely, that means you can work out that tension in this string is going to be equal to the centripetal force minus the weight of that ball or of that object, which is really nice because it means you can work out what the tension in the string is at this point on the circle. Now, obviously, we've got a couple of other situations, and the other most poignant situation is down here at the bottom. Because we've got the opposite scenario here. We've still got a tension. We have to, because the string's what's holding it in place. And of course, the centripetal force is what's important, and we'll call that F2. Please don't be confused here. F2 and F1 always will be the same, because the centripetal force in this situation is the same. I'm just suggesting F2 for a different position. So we've got a secondary tension. But which direction is mass acting here, or the weight acting? The weight is acting directly downwards. So in this circumstance, F2 is going to be made up of T2 minus mg. Because effectively, the tension in this string has got to counteract the weight due to gravity. Because that weight is acting against the centripetal force. So we need to pull up harder in order to make sure that it has enough force to have the same F in both circumstances. So in this case, T2 is going to be the centripetal force plus mg. And that's really quite interesting because obviously that means that the tension in a vertical circular motion, or the force that's creating this, is much greater at the bottom than at the top. So when I'm swinging my object round in a circle, the force is greater at the bottom in the string than at the top. Because it has to be, because it's counteracting the effects of gravity. Okay, so let's have a look at the other two situations here. Now this is a really interesting one. Let's call this T3. So we've got a tension here. And that we've got our centripetal force. Remember, F3, F1, F2, they're all the same value, but our tensions are going to be different. So let's have a look at the tension here and how the tension is going to change. Well, which way is gravity acting now? Well, gravity is acting that way, which is at right angles to that force. Well, as you hopefully will remember, when you've got a force at right angles to another, no component of that force is involved with it. So what effectively we've got here, we've got mg acting downwards and T3 acting inwards, and this means that because mg is at a right angle to T, then no force or no component of mg is included in the centripetal force here. So in this circumstance, F3 would be equal to T3. They would be equal to each other because there's no other force that's acting in the same direction. So that's a really nice way of seeing, if we know the tension, we know the centripetal force in this circumstance. Now there's a fourth and final version on here, and this is possibly the most challenging one, because you need to realize that there's a lot going on here and we need to do some vector resolution. So look what we've got here. We've still got our centripetal force for, please remember, F1, F2, F3, F4, they're all the same value because the centripetal force that maintains this circular motion is always the same. So F4 in this circumstance is going to be made up of a tension, T4, tension in the wire or the string. And is weight going to be involved? Well, here we knew that weight was involved and it makes the tension less. It doesn't need to be as much because weight is acting in its favor. Here, tension is having to pull up more because weight is acting against it. So would you say that it was acting with it or against it here? Hopefully you're seeing that up to this point it's going to be acting with it, and from this point onwards it's going to be acting against it, and then it's going to be acting with it again. So with it, against it. And so as a result here, we're going to be expecting an equation very similar to the F1T1 equation that we have up there. So let's have a look. Let's see if we can work it out. So we know that the centripetal force is going to be made up of a tension and minus a bit of, plus a bit of the mg. But it's not all of mg, is it? Because mg acts in that direction. So we need to find what component of mg acts in the direction that we're interested in. So there's going to be some trigonometry here, so we're missing something here. So in order to work that out, we need to appreciate the fact that we've got a vector triangle being formed. Now be careful. A lot of people would probably go, oh, I can make a triangle like that, and there's my right angle triangle, and I can work out the hypotenuse. Unfortunately, that is incorrect. Because of some of the savvy ones amongst you will remember some of my previous videos, and where I've said the weight due to, or the force due to gravity is always the hypotenuse. So in this case, that must be the triangle there. I'll just blow that up a bit more. So there's our centripetal force acting in that direction, and we've got our weight mg, and then we've got this value here, which is the triangle, and we can suggest that we've got a value of theta. Now it might be for any reason that you might not be given that value of theta, you might be given a different one, and you have to then plan your trigonometry accordingly. But for all intents and purposes, I'm going to suggest we've got this angle right here, the angle from the vertical to the angle of of the force that we're looking at, the centripetal force, in this circumstance. So, a bit of trigonometry will take you to seeing that this is the hypotenuse, this is the adjacent. So if we're dealing with the adjacent and hypotenuse, we're dealing with a cosine value. So cos theta equals the adjacent over the hypotenuse. In this case, cos theta will be equal to the value that I'm looking for, A, divided by mg. And so therefore A is going to be equal to cos theta mg, or mg cos theta. So now we can put in our term mg cos theta. And we can quite nicely see here now, finally, that the force, the centripetal force at this position is going to be equal to the tension plus the component of the weight that's acting in that direction. Making sure you can get that component correctly is going to make a big difference. Being able to know your trigonometry, be confident with it, and remember that golden rule. The weight is always the hypotenuse when finding out components of it. So, finally, we can see that T4 now is going to be equal to F4 minus mg cos theta. And very nicely, we have come to a good stopping point for now. Do have a look at all these equations. Have a look at the different situations that are occurring here and that allow you to work out the tensions at each of these positions in circular motion, because that is going to be pivotal to you being able to explain how the forces vary as things move in a circle. Please bear in mind, some things aren't on strings. Some things like washing machines are being pushed by a contact force. So when you have clothes moving around a washing machine, they're being pushed by a contact force. You might have an airplane moving in a loop-to-loop, and that's being caused by the thrust of the engines. The centripetal force is being caused by that. Obviously, taking into account its weight at every one of these points as well. So hopefully in lesson we'll be able to speak about a few of these and talk about them, and hopefully do some maths on them as well. Remember to bring any questions you have to lessons, and we'll see you soon.